Hello everybody, welcome to this second lecture of week 7 where we deal with controllability and reachability analysis. So far what we have seen is to characterize reachability and the concept of controllability in terms of subspaces of Rn, where my states evolve in Rn. We also had a characterization of what was the minimum energy required when I say I can control a system from any state to the origin, or I can do the reverse, right. I can go from the origin to any point x1 in finite time with application of some arbitrary control input, as long as it is bounded. So, this lecture we will see or we will also so this will also be familiar to what we would have done earlier, called the concept of the controllability matrix. So, whenever we talk of controllability, the first course on state space will tell us about the controllability matrix or the Kalman rank conditions. Okay, so let's focus here on LTI systems, where the equations look a little nicer than that for LTV systems. Okay, so I start with x dot equal to Ax plus Bu with again x in Rn, U in Rk. So we have k inputs for the system. The reachability and the controllability Gramians take this form. Right. So, I can just compute them to be something like this, and so e power at is my state transition matrix for the LTI case. Okay. So, the controllability matrix is defined as the following. So, you have C is B, AB, A square B all the way till A n minus B, and this is easy to check that this is a n cross k n matrix. Okay. Now, what is the relation of this controllability matrix defined here to what we learnt in the previous lecture on the reachable subspaces and its relation to the image of the reachable Gramian, and the controllable subspaces with its appropriate relation to the controllability Gramian. Okay. So, before we do this, I will we can not do a proof of this, but this is a little intuitive. So, the notions of controllable and reachable subspace coincide for continuous time LTI system. So, if I say a system is controllable, it also means it is also reachable in the LTI case, continuous time. So, that's what I will emphasize on. Whenever they are not equal, I will tell you why they are not equal. Okay. And they also do not really depend on the time interval considered. Okay. So, let's check how to prove this. So, I know these two are equal, I also know that these two are equal. So, let me just prove maybe either this or this. So, if I do a proof for this, this will follow immediately and vice versa. Okay. So, let's start by showing that if x1 is in the reachable subspace, which is also equal to this one, then x1 also belongs to image of C. Okay. So, what is given to me? Okay. So, I need to prove this, that the reachable subspace or the reachable set is the image of WR T0 T1. This we proved in the previous lecture. Now, we also proved that this is actually also the image of C, where C was defined as B A B A n minus 1 B. Okay. So, we follow the same philosophy for the proof, right. Let us first begin by assuming that there is an x1 in R, and we show that this x1 also belongs to the image of C, and then we will do the reverse. Okay. So, we will do this first. Okay. So, first to check this or to verify this, so when x1 is in the reachable subspace, there exists an input u that transfers the state from x at t 0, which is the origin, to x at t 1, which I call as x 1. Okay, which means in the LTI case it looks something like this: t 0 to t 1 e power a b u tau d tau. Okay, so I just mentioned this briefly here, but we have done this earlier. So if I compute e power a t from the Kelly-Hamilton theorem, what I know is the following, that I can write e power a t as the following way: phi I t a I for all t in R, where this alpha 0 t, alpha 1 t, etc. are some scalar functions. Okay. So there's a way to define this. I will skip this step, but these are to do very well with what we did in one of our earlier lectures, especially I think in week 3, where we were computing the state transition matrix, or where we were also discussing about the Kelly-Hamilton theorem. Okay, so once I know this expansion of e power a t, well, things become a little easier for me now. Okay, so I can write x 1 of t as summation I equal to 0 to n minus 1 a power I b with okay, the integral t 0 to t 1 alpha I t minus tau u tau d tau. So, this is just by simply substituting this expansion for e power a t into this solution of the equation. Okay, okay, this can also be written. Okay, how will this look for I equal to 0? I will have b here, which is multiplied by I equal to 0 will be integral t naught to t 1 alpha naught t minus tau. So, this will be t 1. T 1 minus tau u tau d tau. Okay. Similarly, when alpha, so when I equal to 1, I will have a b, and similarly here I will have t 0 to t 1 alpha 1 t 1 minus tau u tau d tau, and so on. Okay. So, until I go to a n minus 1 b, where I will have t 0 to t 1 alpha of n minus 1 t 1 minus tau u tau d tau. Okay, now what does this mean? So, this is my controllability matrix C, which I defined here, this one. Okay. Now, what does this expression tell me? If I just write it, so this is x 1 of t is C, let me just call this some vector, say alpha, C times some alpha, right. All these are numbers, and then they just constitute a vector. Okay. So, this means that this x 1 comes as a result of this vector alpha transforming via this map C 1 or this linear transformation, which means that x 1 is also now in the image of C. So, this x 1 which was in the reachable set, we now proved that this x 1 is also in the image of C. Okay. So, if I again just write down x 1 is in R, is also in image of C. So, the first step of the proof, well, is now complete, right. We showed this one by making use of this expansion of e power a t. Next, we will show that if x 1 is in the image of C, this will actually mean that x 1 is also in the reachable subset or the reachable set of the system, or this R is also equal to the image of W R. Again, we use a property like this. Okay, we will derive this what this mean. Okay, so the second part of the proof, we start from x 1 belonging to the image of C and show that this actually implies that this x 1 also belongs to R of T 0 T 1, which is also equal to the image of W R T 0 T 1. Okay, so how do we do this? When x 1 is in the image of C, there exists a vector V which belongs to R k times n, right. So, that is how the controllability matrix dimensions look like, right. So, this is a n cross k n matrix. So, there will exist a vector of from R k times n such that x 1 is this C times V. Okay. Now, we need to show that this x 1 is also now in the image of W R, which is my reachable subset. Okay. Now, I know again that this is true, that the image of W R is the kernel of W R T 0 T 1 with the orthogonal complement. Okay. So, very similar to what we did to prove this equality, we will use exactly the same steps. So, when I say that okay, the x 1 is in the image of C and I need to show that x 1 is in the image of R, which means we need to prove something like this. That eta 1 bar x 1 is, what is x 1? Eta 1 bar x 1 is C times V equal to 0 for all eta 1 which come from the kernel of W R T 0 T 1. Okay. Okay. Now, to verify this, just pick any arbitrary eta 1 from kernel of W R. So, from if you recollect our earlier proof, we had in one of the steps we had something like this, that B tau transpose phi T 1 minus tau transpose eta 1 equal to 0. This is in one of the last steps of proving this equality, right. So, that translates to saying something like this here, that eta 1 transpose, this in the LTI case is eta 1 transpose e power a T 1 minus tau B equal to 0, and this is valid for all tau belonging to T 0 T 1. Okay. Now, I take the k derivatives with respect to tau, and what I get is that minus 1 power k eta 1 transpose a k e power a t 1 minus tau times b equal to 0 for all tau in t 0 t 1 and k greater than or equal to 0. Okay. So, now I just say that this is valid for all tau between t 0 and t 1, let me write this properly, t 0 and t 1. So, in particular when tau equal to t 1, what I have is eta 1 transpose a power k times b equal to 0 for all k greater than or equal to 0. So, this means that eta 1 transpose c is actually equal to 0, right, because if say k equal to 0, I have eta 1 transpose b equal to 0, for k equal to 1 and so on. Okay. So, when eta 1 transpose c equal to 0, this also means eta 1 transpose c times v is also equal to 0, right. That is what we wanted to show here, right, and therefore, this completes the proof. Okay. So, okay, just to understand this, I think you can just write down each step by yourself and then check what they mean. And once you get a grab of one or two proofs, I think the remaining ones will be much easier to understand and interpret. So, I will spend a lot of time in teaching you proof techniques that will also help you when you read some research papers or you want to pursue some projects in this direction and so on. Okay. So, a sincere advice is to write down all the proofs for yourself and check them step by step. Okay. So, what we prove now is this one, that this is true, and the other part of the proof that image of C is actually equal to the image of WC is a very obvious consequence. It's the proof goes in exactly the same lines. Okay. Now, we come back to our examples. So, I can start with that parallel RLC circuit and check, okay, what is the rank of the controllability matrix. The rank of the controllability matrix, well, the C takes this form, 1 over R1 C1, 1 over R2 C2 and so on. Okay. So, what happens when both the branches have the same time constant, then C takes some form like this, okay, and therefore, R of C, which is equal to the image of C, will be something like this or just of dimension 1. However, when the time constants are different, so this case we already inferred earlier. Now, we are just computing it via the controllability matrix. So, when the time constants are different, C is non-singular and therefore, image of C is R2. In this case, the image of C is just R1, right, in the first case, right, because C is non-singular and therefore, the image of C will be R2. Image of C is also equal to the controllable subspace and also equal to the reachable subspace. Okay. So, what does this now have to do with, say for example, this quantity here or this thing here where the image of C was only equal to R? What does this have to do with controllable systems? Okay. Now, let us formally define the notion of controllability. Again, I start with a LTV system. So, given 2 times T1 greater than T0 greater than or equal to 0, we can say that the pair AB is controllable or completely, we start with reachable, completely state reachable if R T0 T1 is Rn or if the origin can be transferred to every state. right. So, in any point in the state space. Similarly, I can say about controllability, given two times t1, t0 greater than or equal to 0, or I can say that the pair AB is completely controllable if the dimension of controllable of C is Rn. That is, if every state can be transferred to the origin. So, the first statement or this definition means that, okay, so can I go from this point to any point in the state space, any arbitrary point, any bounded point in the state space. In the second case, it means that can I transfer any point starting from the state space to the origin here, starting from here to the origin, starting from here to the origin. Okay, so what is this? What is the interpretability of this? Well, in case of in case of this, where the time constants were equal, what we could check is that the only possible points that I could reach were on this line, and if this was x1 and x2. Okay. Whereas, if the system is completely controllable, then I should be able to reach any point, or I should be able to come back to the origin from any point in R2 in this case. Okay. Now, how do we check this? Well, the linear system is controllable if and only if the rank of the controllability matrix is n. Okay, so one way to interpret this is, okay, what is C? C is of dimension n cross k times n. Okay, so C has n rows, and image of C is therefore a subset of Rn, and the maximum dimension therefore can at most be n. Okay. And now, for controllability, what we know is that image of C should be equal to Rn, and therefore, we write this statement that the system is controllable if and only if the rank of the controllability matrix is n. Okay, is there well, can I look at it in a slightly different way? Okay, so let's take this definition here, for example. So, in this expression, what I have is x1 of t is C with some vector alpha. Okay. Now, what is given to me in this? If I look at this entire expression closely, the initial condition is given to me, which is 0. I know what is x1, at the final state. The final time is this, also possibly given, this is also a finite number. A is given to me, B is given to me. Okay. So, I can compute these alphas because these alphas directly come from e power at. So, once I know e power at, once I know A, I can compute what are these alphas. So, what is unknown here? The unknown here is, does there exist an input u which will steer my system to x1 in some finite time t1? Essentially, I am solving for an equation like this. So, when is this equation solvable is, well, this alpha is C inverse of x1, and this alpha has the information of my unknowns, which is my input. So, this C, which is a controllable matrix, for a solution to hold here, the C matrix should be invertible, right. Okay. This is a little interpretation when k equal to 1, even though, okay, for higher case it may have a different interpretation, but all the undergrad texts on control will start with deriving the Kalman rank condition of this form, right. When you want that the inputs are just scalars, just u is in R, then I can interpret this as just solution to a linear equation, which is possible if and only if C is invertible, right. So, and which now generalizes to the case when u is in some Rk, to saying that the C must be of full rank. So, what is the full rank? The full rank has a maximum possibility of being n. Okay, so I just start again with the dynamics of the cart pendulum system, which was discussed in the first lecture. The we derived the dynamics to be of this form. It will have certain equilibrium points, right. So, with that is, which means that the pendulum is in the upright position, and also with the pendulum being in the down position. So, this is an equilibrium position for any x star. So, with theta equal to 0, and at steady state the velocities will go to 0. So, this will be the theta equal to 0, the velocities both being equal to 0. Another possibility is just a downward position, right, where theta is pi, some value of x, and the velocity is going to 0. Okay. So, just to do a little approximation, I just approximate sin theta as theta for and cos theta as 1 for the theta and theta dot being close to 0. Okay, now I can ask a question: can the system be moved from one stationary point to any other stationary point by application of forces through the wheels? Then okay, I compute the determinant of this matrix, which turns out that for finite value. So, if as long as this does not hold, which implies that the determinant of C is not equal to 0, which turns out then that the rank of C is 4, and therefore, the system is controllable. Okay. So, just some steps to how to check whether or not the system is controllable, and if it loses controllability, at what point does it lose. But in general, for all these systems, we call them to be generically controllable or even structurally controllable, because for almost all values of parameters of j, m, small m, l, they are controllable except for a very small set. Right. Similarly, even the RLC circuit, right, that was controllable for all values of r and c except when this was true. So, these are systems which are structurally controllable, which is a property directly related to controllability, but a weaker notion of controllability also, where the system is controllable for all parameters except some very small values of parameters. So, as long as we can avoid those, we can steer the system from any point in the state space to any other point in the state space. So, we will not deal with the literature on structural controllability, but you can just dig out something from literature that also turns out to be a very interesting ideas, right. And then they do a bunch of stuff starting from graph theory and all. We will not really touch upon that, but if anyone is interested, I can point you to the appropriate literature. Okay. So, that concludes our discussion on controllability matrix and what are controllable systems. In the next lecture, we will see, okay, so one test that we did today is about the rank of C being n or C being full rank, right, or in the one dimensional case where this where there was scalar inputs, the problem translated to C being an invertible matrix. Now, are there any other tests of controllability? Right? Are there any other tests relating to the Lyapunov stability properties that we studied in the previous lecture? So, that all will be coming up later in lecture number 3. See you then. Thanks for listening.